So today we're going to be talking about electrical power. Electrical power is found by doing current times voltage, or power. Here's the equation. So power is current times voltage. We could write it here with the abbreviations of I for current and V for voltage and P for power. The unit that we use for power is the unit of watts. You've probably heard that as far as the watts of a light bulb. So there's a couple different ways we can think about power. One is that it's a rate at which electrical energy is transferred in a circuit. We'll talk more about that particular definition later in this presentation. You could also think about it as the rate at which that energy gets supplied and used. I find for my students, because they're a little bit on the younger side to be learning physics, an analogy helps. So you can think of power as how much current is flowing in a circuit and how hard it is flowing, like what's pushing it. And if we think of water, that helps us to understand at a more like intrinsic level. So here we've got a super soaker, and not much water comes out. So the current would be low, okay? But there's a lot of voltage. We can really pump that air in there and make there be a lot of pressure to push that little bit of current that there is, okay? Here we've got a hose, and there's a lot of water flowing, but not much pressure. So both of these situations can actually result in the same amount of power. So you can get, the power would basically be measured by like how much you turn this water wheel, okay? But you can imagine you could turn the water wheel effectively with either method, using either the super soaker or the hose. It's just you're doing it in a different way. In one situation, you've got a lot of pressure, but not much current. The other situation, you've got a lot of current, but not much pressure, okay? So let's compare that to actual electricity now. So again, here's our equation. All right, so here we've got an example with circuits. Voltage and currents can be combined in different ways to get the exact same power. So in both these situations, the objects have 60 watts of power. You'll just see in the one with the big light bulb, we have a lot more voltage. It's 120 volts. That's going to be more like the voltage in your house, okay? Where in the other one, we've got a 12-volt battery, which is more like a car battery, okay? But you can see the current is going to be different, and that's what results in the power being able to be the same, is because we change the current. All right, so here are different light bulbs, and you can see that they're telling you how many watts each one utilizes. So even though they're all plugged into the same circuit, they all have the same wattage, which means they have the same power. So what's different? Well, power equals current times voltage. The voltage has to be the same because they're all plugged into the same circuit. So what's different? The current. How much current each one of these light bulbs draw. In a different video, explore what these different light bulbs would do to the cost of electricity. Like, what are you going to pay in your electricity bill as a result of which light bulb you choose to have in your house? Okay, so I've been teaching electrical power for many years, but it still didn't really make sense to me. So I spent a lot of time doing some additional research about other ways to think about power. So I liked this one. It said, it's the rate at which energy is transferred into another form. So basically, all right, your electrons are given energy by the battery. The battery is like providing the push, remember? And as those electrons flow through the circuit, they're going to bump into other atoms. We talked about that when we talked about resistance. They're bumping into atoms. That's going to slow them down, and then they give energy off when they do that. They're going to transfer their energy into heat or to light. So if you look at the words that I highlighted in yellow, we've got voltage and current and energy being transferred. That's kind of the equation of power, isn't it? Because power equals current times voltage, right? And we're looking at the rate at which energy is transferred. So that made the definition make a little bit more sense to me. Here's another way to think about it. All right, so current is basically a measure of how many coulombs of charge are passing by in a second. Okay, so how many electrons are passing in a second? Where the voltage is going to be how much energy was given to each one of those charges. So power is the rate, going to be the rate. It's going to be a combination of how much energy they have and how many electrons are flowing. Okay, how much push behind them. So that also made power make a little bit more sense to me when I think about it. Okay, well, what does current really mean? And what does voltage really mean? That helped me to make a little bit better sense of that definition. So I will post another video here that is showing some example math problems related to power. And if you found this video helpful, please give it a thumbs up or subscribe to find more videos like this. Bye-bye.